So Norton's theorem circuit analysis. What this is one way of analyzing a circuit, and then in a way of simplifying the circuit. Okay, what this theorem says is that if you have a circuit of this form, this right here, right, this one, it could be that there are other elements here, but then let's make it simple. If you have a circuit of this form and then you want to actually see what's happening in this side, where this side here you have, let's say, other sources and the resistors there, but then your interest is to be able to know what exactly is happening, right? What exactly is happening when you look within this side, right, from this direction, like looking at these terminals, right? So that's what it's saying. But then if you're able to go through the procedure and then follow through, you'll be able to simplify the whole circuit and then get what do you call it, a current here. So this symbol is actually a current source or current generator, right? So simplifying it will give you this. So you have a current generator here and you have the resistors, so right, because other sources. So we have a current generator here, or a current source, and the resistors all simplified to this. But then this current here, because you are looking through this terminal, still appears here. Okay. And one thing we should notice that whatever we represent here, the representation we're having for the current in the simplified form is actually a closed something. So you look at this very well. This line here, this green line here, touch the terminals, right? So it's actually closed. It's not open, right? So current can flow through that side. Okay. So that's the current there. So now, as I was saying, element can be here, right? Okay. So we know that this Thevenin's theorem, and then this is how it simplifies everything. But we're going to use an example to understand how this works. Okay. So the example we see below is asking us to find the current in the 2 ohms resistor. Okay. Okay. So now we are done with this one. So let's move up. This example here is asking us to find the current in this. So our interest is a 2 ohms resistor. This is just one here. So it's asking us to find the current in this 2 ohms resistor here. Okay. So that's how we do it. So for the Norton's theorem, what it says is that whenever you're trying to find the current, so you see this one, we are trying to simplify this, and then we're trying to simplify the two, right? This and then this, and then you end up getting something straightforward here, right? Okay. So what Norton's theorem says is that if you're trying to analyze what happens within a particular branch, then again the question was like, we should find the it was actually the voltage across. If you're trying to find the voltage across this one here, the 2 ohms that we see here, right? Meaning that our branch of interest is just this side, right? So the Norton's theorem is saying if you want to find what is happening within a particular branch, what you do is that you actually do a short circuit at that side. So I'm just going to do it before, so it's something like this. Okay. So, and then one important thing is that whenever you look at the circuit and you're trying to analyze it, be very careful of the value. So in this example here, you see that we have 20 volt, 10 volt, but then the resistors are in point, they're in decimals, right? It is very important that if you want to avoid any mistake at all in with the calculations, you change that one, or you change it and you make it just 4, right? So that you don't get confused and be turning the 0.0 thinking that it's maybe around 40, right? So let's clean that up. Basically, we're trying to, this is what they call data engineering also. Yeah, data cleaning. I'm trying to make the data clean. This is by the way though. Okay. So now that I have this, I know these are just simple numbers. Okay. So what the Norton's theorem is saying is that if you have a circuit of that sort, and then you're trying to find what's happening in the branch, which we know we are trying to find the voltage across these two here, but then this two is in this branch actually. So what we do is that we short circuit that branch. That's what it means. That's what we do here. So okay, we're going to short circuit that branch. Short circuit means that you put just a wire there, right? Just a wire. So meaning the resistance there is what? Literally 0, right? We've discussed this. So this, well, the understand is not clear. You can take the introduction discussion here. So we short circuit this side. Okay. Then again, when we said that when it comes to apply electricity, one of the basic equations is what V is equal to what IR, right? And then when we look at the Norton theorem, what did we say? That when we simplify it, what we end up with is a current source, right? It's a current source or current generator and then a resistor, right? And then we've been saying so far that the easiest of these two to find is usually the resistance, right? And then, so we are going to find the resistance rate for it. When finding the resistance, this is what happens. The effective resistance. We eliminate any other thing. So if there's a resistance here, we have a closed circuit here. And then we have this, the resistor is here, right? This here. So this is how we do it when we are trying to see the effective resistance. So clearly these two resistances are in parallel, right? So if we are trying to find the effective resistance, so the effective resistance, it's just the resistances here are just 4 and 8, right? The simple circuit that we have right now, the resistances there are just 4 and 8. Okay, so if it's 2, product for sum, so 4 plus 8, and the effective resistance here, that will give us, because we are following this basic equation, we said our aim is to what, in the end, try to be able to find the current here, right? Yeah, the question actually asks for the voltage across a particular the 2 amperes, right? But then because it's doing a branch, we have to be able to find the current across the branch, and if we know the resistance, we'll be able to find the voltage across that too, right? So this is what we do. So then we said that R is easier to find, so this is what we're trying to find. So this is what we have. So the effective resistance there will be 2.624 dp, right? So let's make it 667 ohms amperes. So ohms. Clearly have the resistance now, the effective resistance, right? So we should be able to find, so we have the resistance, we've dealt with that. So we should be able to find the I, right? And then because we break down the circuit, we're having this, we've done strict circuits and everything, meaning that this voltage source, right, current in direction, there'll be a current here. So let's see about I, let's make it 4, right, because of this 4 amperes, right? And then a current here, right, let's make it I8, right, because the current passing through the 8, right? So this is how it will be. But then our interest is what's actually happening here. So to do that, what we do is that we should be able to find this one, I4 and I8 individually, and put them together, and we get the current that's passing through this one. So that's what we do. So let's see, we know V, then again, the general equation V is equal to IR. I keep on writing this because it's very important that we keep this in mind. So we're trying to find current, right? So current, so we need a V and then we need a R, right? We have the V to be 10, and then we have the R to be 4, right? So let's see what that gives us. So we have a 2.5 amperes, right, which is for I4. Okay. So now our I8 will be the same V on I is equal to V on R. That will be 20 on 8, right? 20, right? 20 on 8. It could be about the same. Yeah, 2.5 again. So we have a 2.5 amperes here as well, right? So what this means is that the whole current, or the current that is passing through this side, this IS here, so the IS, right, which is the current passing through our branch of interest, right, will be the sum of the I4, right, and the I8. The labeling, you can make it any way you want, but just that you should be clear with your labeling. Okay, so we end up getting 2.5, that gives us 5 amperes, right? 5 amperes. So that's the current passing through our branch of interest, right? We found the IS. So let's go back to the original circuit, right? So our aim was that we get a circuit like this, complex like this, to simplify and get this. And then we need 3 things, which we've identified here already, right? So, a minute. We need this current here, we found this, right? We need this effective resistance, we found this. And then the current passing through this one, actually, the whole one here is actually being generated by this 5 here, right? But then now we're going to put in an element. This was just for an illustration, but this is the whole concept, right? We've done the effective resistance, and then we found this current from the generator, right? So now we are going to split it because there are two elements here, right? We now have to find a way to see which one goes to the two. So now let's see how we go about that. We have to copy the modified circuit, which is something of this sort. So let's see. So this one. We have most of the values already. We just need one last thing to be able to find the voltage across the 2 ohms resistor. Okay. Oh, let me just this what we need. This one. Okay. So now because we found this IS already, which is the actual value for here, we had that to be 5 volts, right? And then we had this resistance here. Let's see, that was about 2.6667. So let's say 2.6667. That's ohms, right? Okay. And then this I here, because there's just more than one element there, we're just going to put everything there, right? So we'll still keep it in green to know that these are what we are looking for. So just one. So okay. We have this, right? And then there was an element here. There's one resistor here, right? And then we have this, and then we have our resistor of interest, which is the 2 ohms. So let's make it this one to show this what we are looking for, right? Okay. Okay. So this is 8, right? 8 ohms, right? And this is our 2 ohms, our resistor of interest. Okay, so this is what we do. So now we found this 5 volts here, but then this is the only voltage source here, right? So as current moves, let's see, a minute. As current moves, it moves in this direction, but when it gets here, because there's one resistor here and a resistor here, actually split, right? So we get a current here, so current division. So if our aim is to find the current, our aim is to find the voltage across the 2 ohms, something like of this sort, right? We should be able to, V is equal to IR, right? So meaning we should be able to find a resistor, which we know to be this 2 ohms here, but we need a current, right? But in the current, this current from the 5 here comes here and then it splits to these 2. So we should be able to get the amount of current that flows here. But then when elements are in series, the current that flows through them is the same. So when we find for whatever is happening here, we should be able to find what passes through the 2, and then we get a V. So that's what we do. The current through this branch here, this one right here, this is what we do. Current division. So if we've been following so far, that's how we go about it. That the current through that branch, which is end up being the current through the 2 ohm resistor, will be what? The other, this one here, this resistor, which is 2.6667, all on 2.6667, right? But then we add something. What do we add? We add whatever it is that is here, right? But this one here actually is series, so we can add them straightforward. So that's about 8 plus 2. That gives us 10 ohms, right? But then we multiply by the total current that's coming, right? Which we found to be 5 amperes, right? Oh, this is a current. So this is a current source, so it should be 5 amperes. 5 amperes. So this 5 amperes is being shed, right? So this was what will give us the current flowing through the 2 ohms resistor. So let's see how we get 2.6667, right? 2.6667 plus 8. Okay, let's put them together. Plus 2 times 5. And that gives us 1.0526 amperes, right? So this is the current passing through the 2 ohm resistor. So now that we have R, we have I, we should be able to find the voltage in the across the 2 ohms resistance, right? So V2 ohms. The I is what we have now, which is the 1 point. Let's just write this in 2 amperes, right, times the 2 ohms, right? So we have this. So let's see. To know. Okay, so that's 1.0526, right, times the 2, and that gives us a voltage of 2.1052 volt. So this is the voltage across the 2 ohms resistor using the Norton's theorem. Right.